This is a production of Cornell University.
Well, thank you all very much. Thank you, Mike, for the invitation. Thank you to all the faculty and students that I met with today. I appreciate your kindness. I appreciate your hospitality very much. I'm Lou Ziska. I used to be with the Crop Systems and Climate Change Laboratory. I am now with the Adaptive Crop Systems Laboratory, and I will leave it to your imagination to determine why that it might be. I have a lot to talk about today. I wish, in all honesty, that I had an entire semester to talk about climate change and CO2 and food security, but I only have about an hour. So I'm going to try and condense that entire semester into the next 55 minutes or so. I will give you a midterm. There will be pop quizzes, and there will be a final exam, so that you feel like you've actually gotten an entire course worth out of this. Let's begin with some definitions. The obvious one is, what do we mean by food security? Basically, there has to be an adequate supply. The food has to be safe. It has to meet dietary needs, and it has to be available. As agriculturalists or plant scientists, we focus, understandably, a lot of attention on production. But the food also has to be safe. The food cannot contain pathogens. It cannot contain contaminants. It has to be safe to eat. The food also has to be nutritious. It has to be able to supply enough energy and vitamins and minerals in order to support an active lifestyle. And finally, the food has to be available. It has to be equally distributed. And I bring this up because this is something that I've experienced firsthand. My father was in the military, and in the beginning of the month, we ate very well. But by the end of the month, not so much. I don't say we invented meatless Mondays, but we invented meatless Tuesdays, Wednesdays, and Thursdays. Right now in the United States, about 1 in every 6 children goes to bed hungry every night, and I find that unacceptable. I hope you do too. The extreme form of food security or food insecurity is famine. And since the onset of civilization, famine has accompanied food security or insecurity. I won't go through all the hundreds of examples of famine. I'll focus just for a moment on the ones that occurred in the first half of the 20th century. Those in Russia, which killed approximately 17 million, China, 36 million, India, 3 million. To put this in perspective, today about 8,500 children die every day because of starvation. They are simply not getting enough of what they need in order to live a proper life. When I say starvation, what happens is that those children die not because they're not getting sufficient calories, but often because they become so weak that they become targets for opportunistic infection. To give you some perspective on this overall, the estimated deaths from World War II were about 55 million. The estimated deaths from famine from 1900 to 1970 were 60 million. It has been, as far as civilization is concerned, just simply the cost of doing business. This all changed in the 1960s. In the 1960s, we were looking at a crisis. We estimated that the globe could only hold about 3.5 billion people. And we saw from 1900 onwards that the population was quickly approaching that particular threshold. And the idea of a dystopia where people would be starving very much led to a change in the social media of the time, from movies like Soylent Green, to books like The Population Bomb, to television. This is The Mark of Gideon, just a Star Trek episode, season 3, chapter 16, and yes, I am a Trekkie. But that really caught the imagination of everyone, that somehow we were going to have this dystopian future where there would not be enough food. And yet, today, there are 7.5 billion of us living on the globe. WTF, right? The F stands for food, folks. Come on. All right. What happened? What changed? Well, 2 things. The first was an invention by Fritz Haber, known as the Haber-Bosch process, taking nitrogen out of the air and converting it into ammonia, into fertilizer. And as you can see from the right-hand graph, the amount of fertilizer use has increased proportionally over that time. In the 1960s, it really took off. It quadrupled. And today, I think we're a little over 120 million metric tons of fertilizer use globally. Fertilizer was one of the important discoveries. But the problem was, if you look at that graph, you see that there wasn't much nitrogen use prior to about 1960, and yet the Haber-Bosch process was invented during the First World War. What happened? Well, if you look at this picture, you can see that these scientists standing in a wheat field in Mexico, that the wheat goes up to about their shoulders. And when you gave them more nitrogen, those wheat lines simply fell over. They rotted. So ironically, you were giving them more fertilizer, but you weren't seeing an increase in yield. What happened? Well, the second thing happened, and that is that this gentleman, whom I assume, is there anybody who doesn't know who he is? Right? Okay. This is Norman Borlaug. He is the father of the Green Revolution. And he was able to take the invention, the Haber-Bosch process, and use it by examining the different phenologies, the different structures of wheat. As you can see, wheat comes in different sizes. You have a semi-dwarf wheat. You have a tall wheat. And this was later created from wheat over to rice, with Cush, others taking this idea and applying it to rice. So now, when you added water and you added fertilizer, you got more seed that didn't fall over in the field. And this was, in fact, the basis of the Green Revolution. Of course, you had to use a few more chemicals because in nature, those tall varieties are tall for a reason. They're very good competitors. They outshade the weeds. But if you have a short variety and you have weeds growing, well, you better make darn sure those weeds are taken care of. So the chemistry became part of the overall Green Revolution. Now you may ask, well, gee, this is just wheat and rice. That couldn't possibly have made such a big difference. But in fact, half the world depends on three crops: rice, wheat, and corn. So in essence, the Green Revolution doubled the globe's carrying capacity, the ability of the globe to handle another 3 or 4 billion people. Half of you sitting in this room would only be sitting here, would not be sitting here if not for the Green Revolution. But it does rely on cheap energy to make the nitrogen, and it relies on available water, and it relies on more chemicals. But that's the current paradigm that we have in order to produce the food necessary to support the current global population. Okay? So that's the Green Revolution. We're able to supply enough food. Now let's ask the next question. Can we continue to rely on the Green Revolution to provide food for the additional 1 billion people that we're still expanding every 15 years? We're expecting almost 10 billion by 2050. Can we rely on the Green Revolution to change the diets? Because feed for animals, the first thing that happens when you become economically viable, when you get more money, is that you want a better diet. I want meat in my diet. I want dairy in my diet. I want protein in my diet. Well, it takes more cereals to produce that. There's a cost. And of course, more fuel for bioenergy. So how's the Green Revolution doing with all this? Is it able to keep up with demand? Well, I did an analysis looking at 8 different cereals, including, of course, the big 3, wheat, rice, and corn, but also oats, barley, sorghum, millet, etc. And what's shown in this graph is the decadal percentage change in population versus the decadal percentage change in increase for those 8 cereals. And so from 1960 to 1969, that's 1 point. 1970 to 1979, that's the second point. And you can see from this graph, based on FAO data, that the Green Revolution was pretty cool. We were basically increasing food much faster than we were increasing population until we weren't. So at some point, and there's a lot of variation in this, so at some point in the last probably 10 years or so, the 2 lines have met, and the Green Revolution is, by all intents and purposes, over. And you can really get a sense of this, I think, if you start looking at something like wheat. This is the percent increase in terms of production per hectare for the United States beginning at 1970, end of the Green Revolution, and for the world. We are not able to keep pace with the current population demand. It's dropping. So this is where we are. In the 1960s, we recognized that we needed to do something. The Green Revolution kicked in, doubled our overall carrying capacity. But that dashed line in the last graph is where we need to go. If that's the amount of food we need to feed 9 to 10 billion people before population starts to decline. That's our challenge. That's what we need to do as agronomists and as agriculturalists and as horticulturalists or anyone having to do with plant science. And I fear very much that we are back to those old days of famine being a constant accompaniment to the global population. This is a headline taken from the New York Times a couple of weeks ago. We recognize that the challenges to food security are already severe. Not just for the 10 billion people that we expect, but to maintain food for the 7.5 billion people that we currently have. But there's more. How do we deal with climate change? Right? How does climate change fit into this? Well, what is climate change? We know that CO2 is increasing. It's over 405 parts per million currently. This is the data from Mauna Loa, the longest continuous record that we have for carbon dioxide. We know that CO2, about 90% of it comes from combustion of fossil fuels and cement, about 10% of that from land use change, and then we see where the CO2 goes. About half stays in the atmosphere, half gets reabsorbed by photosynthesis, and about a quarter gets reabsorbed, and about a quarter of it goes into the oceans. This isn't rocket science. If you take a fossil fuel, whether it's coal or oil or natural gas, it's carbon, and you oxidize it, you burn it, carbon and oxygen, CO2. Chemistry 101, right? So these are the CO2 concentrations that we can expect, and I won't go through all the different IPCC projections, just to point out that the bottom green line is the everyone drive a Prius, hold hands and turn your thermostat down line, and the upper line is the actual business as usual line, and that's exactly where we are at the moment. So all of this essentially means that there's going to be an indirect effect of rising carbon dioxide is going to be warmer temperatures. Now, there are a number of different constituents of the atmosphere, but there are two, carbon dioxide and water vapor, that we call global warming gases. Now, to explain global warming, I will, of course, turn to the guitar. How many of you play a guitar? This is your midterm, okay? Great. So this young gentleman back here, if I tune two strings of the guitar to, let's say, A, it's 440 hertz. Both strings are tuned to the same frequency. And I pluck one string, what will the second string do? It's going to vibrate. It's going to resonate. What if I'm a Lutheran? What if I'm a Lutheran? Will it still vibrate? Yeah? What if I'm a Republican? Will it still vibrate? You're not sure? Okay. All right. All right. So you're telling me that the laws of chemistry and physics don't depend on religious denomination or political affiliation. Is that what I'm hearing? All right. Crazy, crazy guy. No, you're absolutely right. So what does this have to do? What does this have to do with carbon dioxide and water vapor? Just this. Just like that guitar string, the molecule CO2 and the molecule water vapor resonate. They don't resonate at 440 hertz. They resonate in the key of infrared. They vibrate. They absorb some of that energy that would otherwise be lost into deep space. They keep the Earth much warmer than it would be otherwise. We've known this. There's the idea that there's the natural greenhouse effect has been known for 150 years. Without CO2 and water vapor in the atmosphere, you would all be sitting around a fire covered in fur, right? But as you add more, there is a sweet spot. There is a Cinderella. There is a, Goldilocks. I get my Grimm brothers metaphors mixed up. But there is a Goldilocks area where too much and too little, all right? So to really understand the physical consequences of temperature and the change that we're seeing as associated with CO2, we have to understand that the temperature increase is not uniform. Why isn't it uniform? Because water vapor and CO2 act in different ways. If I look at the globe, where on the Earth is it warm and humid? At the tropics, right? So adding CO2 is probably not going to do a whole lot in terms of surface temperatures. Now, flip it around. Where is the air dry? Doesn't hold a lot of water vapor, and therefore adding CO2 will have a bigger effect on surface temperatures. That's the equator. Where is the air dry? The Arctic, the poles, right? So we expect to see that the poles are going to be increasing in temperature faster than the equator. In the deserts, the air is dry. We expect to see increasing desertification. So in those areas where it's warm and wet, they're going to get warm and wetter. Those areas that are dry are going to get drier. Those areas that have ice are going to melt. Also with altitude, and of course, if you had to look at Cornell, which season in Cornell is the air dry? Sorry? Winter, thank you. So which do you expect to warm faster, winters or summers in Cornell? Winters, exactly. So we expect to see this disproportionate change in warming temperatures, with winters warming faster than summers. Now, if you understand this basic stuff, you understand that it's going to have an impact with respect to plant biology and food security. You also understand more than most politicians. This is not difficult. This is pretty basic stuff. Any questions on that so far? Because that's pretty much what we're going to go from here. Okay, you all passed your midterms. Let's go for the second reason why the change in CO2 is important. Plants are essential to life. Without plants, life as we know it on Earth would not exist. You've all eaten today. I assume you have all eaten today. You ate plants, or you ate something that ate plants, right? So what happens, what are the four, sorry, I lied. Here's a pop quiz. What are the four things plants rely on in order to grow? Pardon? This is not rocket science, folks. You're Cornell here. You know what the answers are. Come on. Water. What else? Sunlight. What else? Nitrogen, nutrients, right? Okay, nutrients. Now, suppose, just suppose for a moment, let's pick nitrogen. Somebody mentioned nitrogen. What if the amount of nitrogen since 1970 had gone up by 30% all over the world? Every soil that you know had gone up by 30% more nitrogen. Would that have an impact on plant biology? Yeah. Here's a $64,000 question. There are 435,000 different plant species. Would that increase in nitrogen affect them all equally? No. No. Would you want to study that difference? Should you be studying that difference, since it's affecting all life on the planet? Yeah? Fair to say you would? Of course. Well, in fact, carbon dioxide has gone up by 30% since 1970. How many of you are studying carbon dioxide effects on plant biology right now? See a show of hands. One. Bless you, sir. I went to the ExxonMobil website, found this picture. Here's what happens with more CO2. And this goes along with the CO2 is plant food. Yay, plant food. It makes loblolly pine grow more. Yay. Well, the website actually didn't say that when loblolly pine grows more, that the wood becomes weaker. They kind of left that part out. So, yay. they kind of also left out the part where CO2 and climate change makes the plant defenses less. So, yay. And of course, CO2 is not a very smart molecule. It also affects things like poison ivy. It also affects weeds, plants you don't like. Or in the current administration, I guess they're not weeds, they're alternative crops, okay? They're just alternative crops. So we've actually studied the impact of CO2 on poison ivy. We did this at the Duke Forest, working with Jackie Moen, who's now at the University of Georgia. And in fact, we find that poison ivy grows more, and it produces more erythritol. That is the chemical that causes the contact dermatitis. So when you say or you hear that meme, CO2 is plant food, yay, please think about it. Green is not necessarily a good thing. If I have 435,000 plant species and they're all going to respond differently and I have no idea how they're going to respond, and I know that's going to have an effect both on the environment and on my ability to feed myself, yay is probably not the proper response. All right. You've had the definitions. Let's put these together now. Food security and climate change. The physical effects with respect to water, temperature, energy. Biological effects with respect to weeds. Food safety, looking at contaminants, nutrition, protein, vitamins, distribution, and extreme events. There are more interactions, but I'm limited in time. So let's go through these. Okay, you've had a tough week, right? You've had your final exams, and you're going to go to the local steakhouse, and you're going to sit down, by God, and you're going to have a really good meal, right? I'm going to have the best and the rarest T-bone steak I possibly can have, and I'm going to have a salad and some beer. How much water have you consumed? $5 gallons? 10 gallons? Any guesses? 100. Okay, do I hear 200? Do I hear 3? Okay, let's go through the numbers. The beer takes about 20 to 40 gallons of water that are transpired in order to produce the barley and the hops to make the beer. The potato takes 20 to 30 gallons. The slice of bread takes 20 to 30 gallons. The salad takes 40 to 900 gallons, and I should explain that depends on what you put on your salad. Okay, so it can be just plain lettuce, or it can be something really fancy. And the steak takes between 2,500 and 5,000 gallons of water. Ag depends on water. 75% of all the world's fresh water is used in ag. It is the most important resource. We use a lot of water in ag because plants use a lot of water. Leaves transpire a great deal of water. It's about on an average, about anywhere from 500 to 1,000 molecules of water for 1 molecule of CO2. And just to give you some sense of the water intensity, going from beef down to potatoes. Where you eat on the food chain makes a huge difference in how much water you consume. Where does ag get its water? Well, it gets it from a number of sources. But one of the most is rivers. I grew up in Southern California, not far from the Colorado River. And it starts in the lower part of the Rockies, flows through the Grand Canyon, and provides the border between California and ag. Now, in Southern California, you learn to appreciate different shades of brown. There is no real green there to speak of, until you go to the Imperial Valley, where you see acre after acre after acre of lettuce and other things that are being irrigated from the Colorado River. And that's the Colorado River just before it goes into the Gulf of Mexico, because every ounce of that water has been taken out for ag before it gets there. That's the Rio Grande. Sometimes it flows to the Gulf of Mexico, sometimes it doesn't. Other rivers that no longer flow, the Yellow River, the Indus River, the Murray-Darling River. All of these either flow intermittently or have stopped flowing altogether to the ocean. All that water goes, for the most part, into growing ag. This is what's happening to the snowmelt and the glaciers that provide the water for those rivers. All of you know this. River flows diminish over time, even as the need for rising temperatures and climate change exacerbate irrigation needs for ag. When you look at averages and temperatures, they're changing quickly, particularly in regard to extreme temperatures. Temperature per se has a big effect in terms of flowering. Vegetative growth has an optimal temperature much higher than that of flowering. And when you add the fact that when they reach a critical thermal temperature, plants no longer reproduce, it is not a question of a declining yield, it is a question of going from full to zero yield with a very small change in canopy temperature. We did some work with rice at Erie, looking at the percent of filled spikelets. And what we were interested in is looking at the effect of CO2. We know that CO2, in addition to being plant food, also causes the stomates to close, which means that it causes less transpiration or less evaporative cooling coming off the canopy. So when we looked at the percentage of filled spikelets as a function of air temperature, what we found was that the elevated CO2 was showing a much stronger response in terms of floral sterility for the same air temperature, in part because of the transpirational change that occurred with more CO2. This is some work that Diane and Susan will probably recognize. But basically, this is looking at the optimal temperatures for a number of different rice lines. That optimal temperature is about 29, 21 degree day-night. The average increase in yield, again, CO2 is plant food, was different depending on the variety. And that black line really stood out. And I'll talk about that black line a little bit more later. But when you look at the CO2 as plant food meme a little more closely, this is seed yield with increasing temperature. Here is the 29, 21 degree temperature plus a 37 degree temperature during floral, that is during flowering. And if you did that, then there was essentially no effect of CO2. Well, for a couple of varieties, if you grew the rice under high day-night temperatures, 34, 26, and then if you grew them under both a high day-night temperature and a high floral temperature, in essence, you are overall reduced the effect of CO2 in terms of plant effects on yield. And that is, the x-axis is the elevated, which is about 600 parts per million, minus the ambient 400 divided by ambient, so it's a relative term. Energy, it takes a lot of energy, as we talked about, to grow food. Nitrogen for corn takes about 200 pounds per acre. That nitrogen does not come out of the back end of a cow. It comes from the Haber-Bosch process, which is fossil fuel dependent. So as oil costs go up, food costs go up. And you can see on the left is oil costs, on the right is food costs through 2012. That's the Haber-Bosch process. It takes a lot of energy and a lot of pressure to make N2 into ammonia. So physical impacts on production include the issue of water. Water is a fundamental necessity for ag. Snowpack and groundwater availability are being threatened by climate change. Changes in floral temperature can quickly reduce yields. That sensitivity may increase with CO2. Finally, food production is tied to energy. If fossil fuel prices go up, food prices also go up. When you look at the biological constraints and the issue of climate change, I won't have time to focus on all of these, but if I can, I'll just look a little bit about weeds. These are the average annual losses in the US. This is some of Dave Pimentel's work, but you can see weeds have both a tremendous impact in terms of loss, but also cost a great deal in terms of control. Weed-induced losses for CO2. This is Canada thistle. Remember, CO2 is plant food, not just for the crop, but also for the weed. In the case of the seed yield from 2007 through 2009, open-top chamber studies, looking at high CO2 and ambient CO2, the over above ground biomass and seed yield declined much more over time for the soybean when it was growing with Canada thistle under an elevated CO2 condition. And I would add that we sprayed with glyphosate at the beginning of every year, using the best management practices for no-till. Pests are a significant limitation to yield. And sadly, they're not included in any climate change or food security model. I hope some of you in this room can change that. Food security and nutrition, CO2 in the plant ionome. We know that based on a number of studies that as CO2 increases rapidly in the atmosphere, that the plants will increase the amount of carbon. That's the red line shown there. But as they increase the amount of carbon, they also reduce the amount of a number of key nutrients. Nitrogen, which is a surrogate for protein, also declines. Protein is shown on the far right. The exception is for leguminous plants like soybean and peanut. They seem to be less affected in terms of nitrogen concentration. But there are literally hundreds of studies, including 3 major meta-analyses, showing that as CO2 increases, protein concentration declines, along with concentration of key micronutrients. This is some work that I've recently been involved with, looking at free air CO2 enrichment of rice, both in Japan and China. This is the percent change in protein relative to ambient CO2. This is over 18 different rice lines, including Japonica, Indica, and several hybrids that are currently being grown. I think we estimated that about 50 to 60% of all the rice lines currently being grown in Asia were represented by most of these lines, or represented by at least one of these lines that we grew. So this is the change in protein. This is the change in iron that we saw. This is the change in vitamins, vitamin B1, vitamin B2, vitamin B5, and vitamin B6. This is all, sorry, vitamin B9. This is all done on brown rice, unhulled, raw, uncooked. But you can see that this was done only on the Chinese lines. We didn't have the data for the Japanese lines. But in every case, there is a significant effect in terms of reducing the overall protein concentration for the B vitamin complex. Conversely, we saw an increase in alpha tocopherol and vitamin E. Now, we kind of asked ourselves, well, what the heck's going on here? Why are we seeing an increase in some and a decrease in others? And we think this relates to what's happening in terms of the plant ionome. If this carbon-nitrogen ratio is changing, then those compounds, those secondary compounds that have a lot of nitrogen, are going to be the most affected. So what we found was that tocopherol, which has no nitrogen, actually went up, but vitamin B9, which has the highest ratio of N to the vitamin in terms of molecular weight, was the one that was most affected. I'm not saying this is an explanation. I'm just saying it's an interesting observation that we think is consistent with the observations that we saw previously with CO2 and vitamins. Pathogens. Here are some of the common food pathogens: Salmonella, E. coli, Vibrio. We know that each year 1 in 6 Americans gets sick by consuming contaminated food or beverages. When climate change, particularly with rising temperatures, we expect that to be exacerbated. We expect it to be exacerbated at a time when the Food Safety Inspection Service is having its budget cut. I'm sure it's just a coincidence that the 15 largest major food recalls have all occurred since 2000. So for every degree the ambient temperature rises above 6 degrees Celsius, the occurrence of foodborne salmonella poisoning increases by 12%. Storage and spoilage are important determinants as part of the food chain. You can extend the life of food based on its ability to prevent pathogen or fungal infection. But when temperature rises, that becomes more critical. And if you look at things like major power outages associated with climate change, that tended to be going up over the last several years. And of course, typically what happens with that is that the incidence of food spoilage increases and the number of ER visits as a function of food safety, that is, ingestion of spoiled food, also goes up quite quickly. So that's another issue that we need to pay attention to. Some work I did on pesticide contamination, particularly on the role of warming winters on pest biology. My basic hypothesis was that as winters warm, you will see more pests, and therefore your yield should start to go down. Now, I did this as a transect, going from the lake states down to the Gulf states, with each of those marked individually. And I used both NASS, or National Ag Statistical Service data, and FAO data. And what I found was that when you went from Minnesota down to Louisiana, and you looked at the average yield of soybean in terms of metric tons per hectare, it didn't do squat. The average yield in Minnesota was the same average yield as it was in Louisiana, even though the minimum temperatures were quite dramatically different. That is, there were much warmer winters in Louisiana than there are in Minnesota. So maybe warming winters won't be a problem. Except when you look at it slightly differently, it turns out when you look at kilograms of active ingredient of all the pesticides that are used as a function of the latitude, then what you find is that from going from Minnesota to Louisiana, there is a precipitous increase in all categories of pesticides. So yes, the yield is the same. However, the yield is the same because you're using a lot more pesticides in order to control those pests. What that means in terms of public health, it's difficult to predict. Health impacts depend on age, genetics, healthcare access, et cetera. But as winters warm, I would venture to guess that there is a good chance that we'll be using more pesticides in order to control those outbreaks. Distribution, 2012, we had the worst drought in a century. The fact that it was so dry that parts of the Mississippi River did not allow barge traffic. And as a result of that, we lost out on several $billions in terms of ag expenses. Access for Hurricane Sandy, access to food and water. Hurricane Haiyan in the Philippines, again, access to food and water. These extreme events have a short but intense effect with respect to food security. So quality and distribution, nutritional quality, especially protein, will decline. Food safety is a concern. Pathogen exposure, chemical contaminants, food storage, and finally, extreme events may threaten food distribution or access. Are we all depressed yet? Okay, excellent, excellent. All right. Let's throw a little hope your way, okay? Yes, crisis, right. Climate change poses an existential crisis, not only for future food security, but for the current Green Revolution paradigm. The crisis, as we know, is also opportunity. What are the things that we can do to make it better? Well, here are some. Resource management technology, polyculture, urban ag, crop genetics, rethinking pest management, and finally, education and communication. Now, none of these are what I would call one-size-fits-all or magic bullet solutions. These are, at best, magic buckshot, except the last one, education. I'll talk a little bit more about why I think that may be the solution to our crisis. There are all kinds of different things that are going on. Solar paneled heat pumps, spout readings, using human waste to recycle it for nitrogen. The middle graph figure is actually the same corn after a flooded, major flood. The corn on the left had drainage, the corn on the right did not. There's so many of those. Satellite information, my own personal hobby horse is to try and get coal converted into biochar, which can be added into marginal soils in order to improve the health of those soils. All of these innovations, all of these technologies are sort of bubbling from the ground up, and they're really cool, and they're really fun, and there are a lot of that going on. Polyculture, this was the farm back in the 1940s, where you had food from corn to feed the cows gave fertilizer to the corn. It was a very basic polyculture. Now, of course, we have energy being provided by the Haber-Bosch process to grow the corn. The corn, however, is now given to CAFOs, or concentrated animal feeding operations, where the cows produce a lot of that, and then, of course, that goes down, washed down to the Gulf of Mexico, where it produces large dead zones, which kill a lot of the fish. Right? That's not polyculture. But if you're a cattle grower, you can add a few cents in terms of putting weight on faster at a CAFO, but overall, your end result is food insecurity, not food security. Modern polyculture has taken many forms. In Asia, it's not unusual to see ducks being raised in rice paddies, where the duck fertilizer adds to the rice, and the ducks take care of some of the things that are, affecting the rice crops. Polyculture, this is a 2-acre farm, I think somewhere in Iowa. They're growing 30 different crops, flowers, everything. And so if one thing gets affected, they have an out. They have a way to recover from it. Polyculture can be practiced in space, that is planting multiple varieties of a given cereal rather than planting one variety. The number of cultivars will depend on the number of severe events. That is to say, if I have a monoculture and everything is fine and nothing's happening to the climate, then I can max out my economic return. But as you have an increase in terms of the number of severe events, then it behooves you to include a greater amount of cultivar diversity so that you can basically ensure for any extreme event that might happen. Crop polyculture in time, which we would call crop rotation, that also can be an effective means to begin to increase your resiliency. So rotation may decrease input costs, maintain yields, increase resiliency. Urban ag, this is one that is really catching on, I think. Being able to grow crops in the city as a means for educating. We've done this, what we call the Student Discovery Garden at USDA. And I'll tell you what, when you have a kid from the city come out and pull up a carrot for the first time and look at that carrot like, where in God's name did this thing come from? This is what a carrot is. It's pretty cool. It's really emotionally satisfying. Job opportunities, chance to remove some of the, or provide fresh fruit and vegetables for food deserts. There are a lot of opportunities for this all the way around. Crop selection, this is one that I've been working on for a number of years. How do we select crops? Well, pretty much like that. How many of you go to McDonald's? You're among friends, it's okay. Raise your hand. Okay, yeah, I like their fries. I confess it, I like their fries. But all their fries come from russet Burbank potato. 90% of all McDonald's fries come from one variety of potato. That's great if the climate's not changing, but what happens if the climate changes really fast, right? Well, you can see the effect of the Green Revolution in terms of US potato production, but you can also see starting from about 1990 onwards that there are more ups and downs in potato production. These kinds of ups and downs are happening all over ag, more ups and downs than your average honeymoon. So with that in mind, one of the things that we have to do is how do we maintain resilience in our production? How can we be able to provide to food manufacturers ways in which we can have an out so that they don't rely simply on one variety? This, by the way, it's not just potatoes. This is wheat production in the United States, showing the same. This is in millions of bushels, but you get the overall gist. We need to diversify. We need to diversify. So I talked earlier about this particular variety on the top. And what's interesting about that variety is that it's not a variety at all. In fact, it is a weed, Stuttgart, a red rice or wild rice or weedy rice weed. And I don't know why this is not working, but it didn't. Basically, this is an evaluation of 4 different lines of rice, looking at the effect of high CO2 and warming temperatures from 2921, which again is the optimal for rice, to 3325. And looking at the effect of CO2, you can see for 4484, there is an effect under optimal temperatures of CO2 in terms of yield, but it's the Stuttgart, the weedy rice, that in fact is showing the strongest response over a range of temperatures. So by diversifying existing crop lines with their weedy cousins, we may be better able to exploit rising CO2 to increase seed yield. If CO2 is plant food, which I've argued, then maybe we can get it to be plant food not just for weeds, but for crops as well. How do we do that? How do we begin that process? Pest constraints. I'm going to offer this idea. Monitor. We keep track of incoming weapons of mass destruction, like pine bark beetles, right? 35 million acres. Gosh, if only we had, I don't know, some kind of modern device, like a handheld computer. And if we had that kind of device, we could I don't know, we could take pictures of things like weeds, right? And we could have like a global database that we could keep with us on our little handheld computer device. And it would be one that, you know, I don't know, could be sponsored by some chemical company that would actually be able to advertise its product on that. And you could go into it and you could say, look, I have a picture of this pest, and can you tell me what it is and how I might be able to respond to it? Crazy science fiction stuff, I know, but maybe someday, right? Maybe someday. The second aspect of this is mitigation, right? We have what's called an invasion curve. When a weed shows up, it tends to show up in small numbers and then build up very quickly. Anybody know what that weed is? Very good. Bless you. Yes, it's absolutely kudzu. And can you tell me what that weed is? Kudzu, right? Is there a difference between this and that? Yeah. If I detect it early, I can prevent its spread. Once it gets to that, all I can do is weep, right? There's not much I can do to control it. So mitigation depends on early detection, rapid response. That has to be a key aspect of dealing with climate change because things are going to move. The demographics are not going to be the same. Manage. We have a lot of tools in our toolbox. We can no longer just go and spray whenever we see a weed. We have to think about it in terms of what is the weed, what damage is it doing, what demographics are there, that is, do I have one weed, do I have 10 weeds, what tools are available, when should I use them? This is actually harkening back to an old philosophy of integrated weed management or integrated pest management, which got put on hold while glyphosate Roundup became the herbicide that everyone would use, and why were you studying weed science in the first place? So integration of IPM methods to assess emerging climate-driven threats. And finally, and I think this is the most interesting one, research and education. We have to get away from this ivory tower, siloed view of academia. Silos are great. I'm sorry, not silos. Actually, the modern term is cylinders of excellence. So if we get away from this silo approach to how we do science, where we can integrate, where the left eye doctor talks to the right eye doctor, right? That has to be important. We have to look in the context of climate change, and because climate change affects so many different aspects of plant biology, to be able to integrate across different disciplines. Germplasm, genetic information, access and sharing, field trials, better ag statistics, enhanced tech and knowledge transfer, all that has to be incorporated in as a means of breaking apart these silos, cylinders of excellence. Investing in the next generation. Are we losing our best minds in ag? Many of the universities and colleges that I've talked to, particularly in the agronomy department, the number of students are down. And that's true for a lot of different plant science majors. That has to change. We need our best minds, our best people to focus on the challenges that are being faced for food security in agriculture. How can we educate and communicate agricultural science to the next generation? How do we do that? There is a critical need to invest in public research to sustain and improve ag. I went through the federal budget and calculated the overall amount of money that's being spent, both for ARS and for NEFA since 2003. And those are the two lines there. The NEFA line is the dashed line. The ARS line is the solid line. We are failing in our investment in public ag. And it's not to say that investment in private industry can't compensate for some of that, but it can't compensate for all of it. We need to invest in this immediately. And finally, I mentioned earlier that I thought there was one, perhaps, silver bullet in all of these potential means to fight the challenges to climate change. Sorry, I'll flash this, I'm running out of time. And I call it famine and feminism. This is the population growth that we're currently experiencing. Each day, 220,000 people are born, and they all want food. If we educate women and girls, if we offer them the same opportunities that we offer men in terms of their education, in terms of their ability to move forward in academia, then one of the things that happens is that as you increase the amount of education, the fertility rate declines. If we cannot bring population in sync with resource availability, then we can come up with all of the different tools that we want to in order to enhance production or to ensure safety, but we will eventually run out of food. This is not a new idea, but it's one that I think has particular resonance perhaps going forward. That if we can overall realize that half the global population should be educated, has every right to be educated, then we can perhaps bring those issues best into sync. Finally, the science of how we obtain food without destroying the environment that provides it is fundamental to whether civilization endures. That is not post-truth, and that is not an alternative fact. Thank you.
This has been a production of Cornell University, on the web at cornell.edu.